So hopefully you've got a pretty solid handle on the idea of what we're trying to do here. What I'd like to do with the first part of class here is just take some time and write out some pseudocode of how we might structure a code to solve this problem. Okay, so that's what I'm going to do here. Okay, so I'm just going to share my screen and we'll just walk through this, how we might structure this code. Okay, so to start off, let's say that let's see, just a second here. Just going to rearrange some things on my screen here so I can see you guys better. Okay.
Dr. Hunsaker, will you be posting this pseudocode later on?
I was just going to write it out by hand, so it won't be in text format, but I will post this video, so you could come back to this video.
Cool,
so,
thanks.
Yeah. Okay, so here's the beginning of our file, and the first thing we're going to do is want to import a few things. So so for example, I would import NumPy, so that you can use the linear algebra stuff that has built into it. Something that can be helpful for debugging and for visualization is something called matplotlib. So that's a plotting library, and you can import something inside of that called pyplot. And I usually import that as PLT, and I can do PLT dot. And it's basically very similar to plotting in MATLAB, where you say, hey, I want a new plot, and I want to put this on the x-axis and this on the y-axis, and these are my bounds and everything. So anyway, there's a lot of information on online for how to use this this pyplot library. So NumPy, maybe import that as NP, then it's NP dot, whatever you want out of that. And then finally, import math, and I often just import that as M, so that I'm calling that math library M dot, whatever I need in there. So, okay, so I've got some import stuff. These are basically the libraries that you'll need to build this. The way I like to structure code, at least in Python, and Ben, maybe you can correct me or someone else in the class if this isn't a fantastic way to do it, but the way that I've kind of gravitated to structure code is that I put my functions. So I'm going to have a few functions up here. So we're going to, and you start a function by saying def, so you're going to define this function here. So I'm going to have a few functions up here, and then I'm going to scroll down here, and the first actual commands to my code come after these functions. And I'm not sure if this is necessary or not. It seems like in earlier versions of Python it was, because it had to have that function loaded before you could call it. But I may be wrong. Ben, is this not necessary, what I'm doing here?
I don't think so, but I think it's good coding practice.
Okay. Okay, well, that's how I'm going to write this pseudocode today. So you guys can play around with the organization here. But okay, so a couple things that we need. We are going to need a file. So we're going to have to ask the user for a file. So one of the first things we're going to do outside of these functions is we might say I need a file name. So file name equals, and we can call it input. Input, and to the screen I'm going to say enter a file name. So this is the enter a file name for the Airfoil. Okay, so there's that, and then I'm going to assign whatever so it's going to print that out to the screen, and whatever they respond is going to be assigned to this variable called file name. Okay, and then I would do the same for, we want an angle of attack. So I'd call that alpha equals input, enter an angle of attack, right? And we want to tell them, this should probably be in degrees, and so that we know what it is. And then the first thing I do when I come out of that is I'm going to say alpha equals alpha times pi over 180. Right, so I'll get that into radians. And then finally, I need a v infinity or free stream velocity. And so again, I'm going to do that's equal to input and say enter a free stream velocity. Okay. Okay, so this is at the bottom of my file, but it's the first thing that's actually run, because when Python starts, it's going to come up here. It's going to import that stuff. It's going to say, oh, that's a function. There's a function. There's a function. Here's the first executable thing that I do. So it's going to run these. And then let's start off with our first function here. We're now going to call, at least this is the way I would set it up. I would call something called setup. So this is a function that I've written that now is going to take in and actually maybe we want to pass in some of this information like a file name. So we're gonna pass in there the file name to setup. And actually, I think that's all I need, at least for my setup algorithm. It's gonna open that file and get things set up. And then next, I'm gonna call a solve. And for that, I'll probably need to pass in alpha, solve this at a certain angle of attack, alpha and v infinity. And then finally, coefficients. Once that's been solved, I have another function called coefficients that's going to compute the lift and drag, lift and pitching moment based off of this information, okay? So these are the three functions that I have in my code. And so this is just the way that I have my code set up. So, okay, so let's talk about this setup definition. So we've got something called setup up here, and it's going to take in a file name. And so what does setup need to do? Well, it needs to open that file name. So the way I would do this is call something called np.load. So remember, np stands for numpy. I pulled in this numpy library as np. So inside of numpy, it's got this function called load. And I'm going to pass in the file name. And then you can pass in other information. So for example, what I have is I have a delimiter. Delimiter equals tab. So a /t is a tab. And then I have use columns equals 0, 1. So it's going to return those two columns within that file. And there's a flag called unpack, and I'm going to set that to true. Okay, so np.load is going to return two arrays, an X array and a Y array, out of this file that I passed in. If I passed in the correct, or the file in the correct format, which it is in that problem example that I've given you. So now I've got an X and a Y array. And so then what do we do with this X and Y array? Well, let's just talk about this in general. We're going to use that to assign these points to the nodes. Now remember the nodes. So let's draw a sketch of this airfoil over here. So there's my airfoil, and let's say that the panels. I'm just going to do this really coarse so we can see it. Okay, so those are my panels. And the nodes, so we passed in 10 points, and actually each of those points represents a location of one of these nodes. So I just need to store this in some kind of an array. Maybe we just leave it as X and Y, but you might want to put this in some kind of an array where I can just call any of the nodes within that, and it returns an X and Y location. Okay, then we need to compute compute our control points. So the nodes are at the corners of this, but the control points are right inside of that panel, and we're going to use the mean location on each of these panels as control points. Okay, so this is these are control points. So we need to compute an array of those. So we have all of our mean points along those. Okay, and then based off of that, we need to set up our A matrix. I'm gonna need a little more space here. So next we want to set up A matrix. I call this AMAT. Anyway, and so for that, we're gonna be looping over, so we're gonna say for I in range, and we're going to need some variable called endpoint. So we've got to know how many points we've got in our file. So for me, so we've got 10. I'm going to loop from endpoints in this range of endpoints -1, and I need semicolons up here. I forgot a colon here. That colon tells me that that's the beginning of a function or the beginning of something where it's going to be nested inside of that. So I'm going to loop over I, and I'm going to loop over J over the same range here. And basically what I'm doing is I need to loop around and figure out the influence. So for example, I'm going to look at, let's start with control point. Let's call this control point number 0, actually, because this is 0 indexed here. So that's control point number 0. And I've got to loop over all of the panels. I've got, 9 panels on here if I have 10 points. I've got to loop over all of those panels and figure out their influence on that point, right? What the induced velocity is at this control point here. So I need to loop over each of these. I've got to loop over all of these. So for J, so this is going to loop over the panels for any given I control point, and look at the influence of that panel on that point. Okay, so to get that, and then the outside loop here is that I'm going to loop over the control points. Okay, so I'm doing a nested loop here because for each of these control points, I've got to figure out what the influence of all of these other panels is on it. And then I'm going to go to the next control point, and I'm using I to index this. So I is 0 here, I is 1 here. And then when I is 1, I've got to, again, loop over all of these panels and figure out their influence on that point there. Okay, so to do that, I have a function called pmat. And so I'm going to call pmat here, and I'm going to pass in, three things. So for what I'm trying to figure out each time I call this function is I'm going to have some panel over here. So let's just take an arbitrary panel. Let's say that it's this panel right here. I'm looking at the influence of that panel on this control point, right? So that panel is defined by 2 corner points. So I'm going to pass in my two nodes. So node 1 and node 2, and then control point. And actually those nodes, so the first node is going to be the beginning of that panel. The second node is the ending point of that panel. And so I'm looking at the influence of that panel on this control point. And so then we need to pass in the control point of interest. So I'm going to call that POI, the point of interest. Okay, so for each of these, this is an XY pair, right? Node 1 is an XY node 2 is an XY, the point of interest is also an XY. Okay, so we're looping over pmat, and what's going to come out of that is it's going to return something that I call P, and in the algorithm that I've given you that's in Phillips's book and in the handbook that I give you, P is a two by two matrix that's going to be returned here from this pmat call. So I'm going to get P back, and then I just basically store, so a mat at ij here is equal to, and there's some information there in that algorithm, right? What's the at ij, we add some information there, and then at ij plus 1, we put that in. So this pmat stuff feeds into this. Okay, so let me draw that a little better. So the stuff coming out of that pmat call feeds into that. Okay, so I'm running out of space here. Let me move some things. Gonna move this down a bit. And actually, we're gonna cut that. We'll move it down on another page here. Okay. So let's come back up here. Okay, so we're looping through this. We've created our A matrix, and then the very last line of that A matrix, after I've looped through, and I'm actually looping through one less. So I'm going to walk through this big A matrix here. I'm creating this big A matrix. I'm looping through, creating all the stuff in here. Well, the very last line here is where we're going to enforce the cut a condition. Okay, so that's slightly different than what we've been doing through the rest of this looping, and basically that is my final condition here that says that at this point the value of the node on the upper surface and the value on the node of the lower surface, the vorticity there has to sum to 0. Okay, and so we're going to add, after we've created the rest of this A matrix, we're going to come out of this for loop, and we're going to add the cut a condition on the last line. Okay. And then just for good measure here, we're going to print A matrix to a file or to the screen or whatever you want to do. I like to do it to the file because these matrices are going to be big. You know, eventually we're going to have like a 200 by 200 matrix. But for debugging purposes, it's nice to have that A matrix printed out to a file, and then I'm going to return out of this function. So let me just put a little bracket around here. So that's my setup function. So what my setup function did is it read in the airfoil, and then it set up all of the control points, the nodes and the control points around the airfoil. So that's what we did here. And then based off that information, I've now populated an A matrix, and I've set the cut a condition on the last line of that A matrix, and then I return. Okay. So now I have this this A matrix that has been created. Oh, let's talk about this function here. So inside of this, we called pmat. So let's talk about pmat. So I've got another function here called def pmat. And what's that going to take in? Well, it's going to take in an XY point, X comma Y. For this is like a node 1, and then an XY point for node 2, and then XY point for the point of interest. Remember, so these were the things that we're sending in here. Node 1 and node 2 are the first and second nodes, or the two nodes that describe the edges of the panel that I'm looking at. And then the point of interest is that control point, whichever point I'm interested in. So given that information, I've also given you an algorithm to compute the 4 components of P. So we're going to have a P00 is equal to this, P01 is equal to this, P10 is equal to something, and P11 is equal to something. Okay, and then we're going to return P. Return P like that. Okay. Okay, so let's come back down here. So we ran our setup routine, and that set up our A matrix for us. And then the next thing that's going to be run here is a call to our solve function. So let's write a solve function. So we're going to call this solve. And for here, what we need is alpha that was passed in. We need to know the angle of attack and the free stream velocity. We're passing those in there. And so in solve, what we've done here is we've created, if we go back to the big picture here, we've got an A matrix here. That's going to be multiplied by a vector of gammas, which that's what we're trying to solve for. And we're saying that that whole thing is equal to some right-hand side. I'm going to call this a B vector, okay? So this is just an AX equals B problem. AX equals B problem. So what we're doing in this solver is we've got to set up the right-hand side B and then just solve for X or our gamma vector. So we're going to have that X is equal to A inverse times B, right? So you guys are all familiar with that. It's just linear algebra there. So so we've got to set up the B vector. So let's just say we've got to compute the B vector. This is the right-hand side to our system of linear equations here. And then we're going to solve for gamma. So I have mine, I say gamma is equal to numpy. Now, again, this is another numpy thing. It's got a linear algebra solver in there. So it's np.linalg.solve. And I just pass in A matrix, my A and my B vector. And it's going to do A inverse times B and return gamma. And so that's what I get out here. So now I've got gamma, and we might want to print gamma to the screen or to a file and then return. Okay. So again, it's nice to see what gamma is for debugging purposes, for example. Okay, so now we've got our solve function, and so now we have this list of gammas that satisfy this set of equations here that we've set up. So we've solved for gamma, and now finally we've got to use those gammas to compute our coefficients. So let me move this stuff down again. We'll come up with one more function here for our coefficients. So we've got another function called def coefficients. And again, it's going to need alpha and V infinity. And so coefficients in there, we've got an algorithm for computing our lift coefficient, our moment about the leading edge, and our moment about the quarter chord. Okay, so we're gonna compute each of those, print those to the screen. CL, CM, leading edge, and CM, C/4 to the screen, and then return. Okay. A couple things that I kind of skipped over. Again, this is just pseudocode. So we're just trying to lay out, this is the map of what we're trying to do. This is how we might format this code. You don't have to do it this way. You could, instead of having these different functions, you could just have a set of instructions. This was basically a straight linear code in the sense that we never called a function out of order. So except for the P, but so we could have started off this file with the file name alpha and V infinity, and then just copied in the code for setup directly right here, right? We're just calling it once. I like to keep my code kind of compartmentalized a little bit, but we wouldn't have had to do that. We could have not had a function called setup and just put all the setup stuff right in here, not had a function called solve, put all the solve stuff in here, not had a function called coefficients and just put the coefficient stuff in here. So this really, this organization isn't necessary. The one thing that we would need as a function is this P matrix, because we're going to call that a whole bunch of times, right? We're going to be looping over these nodes and control points of interest. So we're going to call pmat a whole bunch of times. So that is the one thing that we would need as a function. But the rest of this, we could have just put in straight up code without using functions at all. Now, because we've used functions, we have to be a little bit careful about how data is stored, because within a function, so for example, I passed into setup, I passed in the file name variable, right? Whatever the user gave me, here's that file name, and I needed that in order to open this. Because inside of a function, I only have access to variables that are passed in or variables that are called global variables, okay? A global variable is some variable that's defined outside of the function. And so I could have actually, should have, there's a couple of things here that I've treated as global variables, and we really would need to define those as global variables in order to use them the way that I've written it out here. So for example, a matrix, I'm constructing it inside of this function called setup, but I need to use that same variable inside of solve, right? So my solve function here has to have access to a matrix. So a matrix really should be defined outside of these functions so that it's considered a global variable, so that the functions inside here have access to it. That's the same with gamma. So gamma is going to be solved for inside of my solve function, but I need gamma. These coefficients here depend on gamma. So gamma again needs to be a global variable. So anyway, I'm skipping over little things like that, but the point here was just to get an outline of what order we solve things and how we would set up this code.